Welcome to AI Paper Slop, the YouTube series where we summarize AI and tech papers so you don't have to, spend your weekend reading them. We are diving straight into today's paper, which is called Qwen-Image-Agent, Bridging the Context Gap in Real-World Image Generation.
Oh, this one is huge.
Yeah, published June 29, 2026 by the researchers over at Alibaba and Qwen. So for the ML engineers and AI researchers listening, here is your quick 60-second core insight.
Let's hear it.
Current text-to-image models fail in real-world production. They are heavily optimized for, perfectly engineered, fully specified prompts, but real-world users give underspecified, implicit instructions. The researchers mathematically identify this discrepancy as the context gap.
Right.
To solve it, they introduce Qwen-Image-Agent. It's a training-free framework that uses a multimodal large language model, an MLLM, to progressively build out the necessary generation context.
Through a whole pipeline, yeah.
Exactly. Through planning, reasoning, search, memory, and feedback. They also built a new benchmark called IA Bench to test this, where this agentic approach jumps from a 17.4% baseline score up to an impressive 45.4%.
Hitting state of the art. I mean, if you are building visual tools for production right now, this paper is a massive paradigm shift.
It really is.
You already know you cannot rely on everyday users to write multi-paragraph prompts. They aren't going to detail the volumetric lighting or the precise spatial composition.
No, the user just expects the system to kind of magically know what they mean.
Exactly. So the burden has shifted. The system itself has to do the heavy lifting of gathering that context. We essentially have to stop treating image generation as a single text-to-pixel mapping.
And start treating it as an agentic system engineering problem.
Yes, 100%.
Let's actually look at the math for a second, because they formalize this context gap really well in the paper.
It's super elegant.
Yeah, when you look at standard diffusion or autoregressive image models, they just run a single forward pass. They are mapping pixels, your Y variable, directly from a probability distribution based only on the raw text you typed in.
Which they call the user context, or C sub U.
Right. But to render a high-quality, accurate image, the model actually requires C sub G, the full generation context.
And the distance between that sparse C sub U that the user types and the dense C sub G that the latent space actually needs to construct the image that is the context gap.
So to cross it, agentic generation formulates a trajectory of states and actions.
Exactly. The system plans, searches, and reasons over multiple intermediate steps to build a final enriched context. They represent this as C of tau, and it all happens before the rendering engine ever fires up.
That makes me think of standard text-to-image models less like an intelligent artist and more like a highly skilled camera operator on a film set.
Oh, that's a great analogy.
Right. Because the camera operator will shoot exactly what is in front of the lens with perfect focus and exposure. But if there is no director breaking down the script, or no location scout finding the sets, the camera operator is just filming empty air.
Or just completely guessing what the scene should look like.
Mm-hmm.
That's a perfect way to look at it, because the first half of the Qwen-Image-Agent pipeline is essentially the director of your film crew.
The context-aware planning phase.
Yeah, and it operates on three distinct levels. First, you have information-level planning. Instead of just passing the raw prompt to the camera operator, the system actually pauses.
It takes breath.
Right. It analyzes the prompt and actively raises explicit questions to identify missing information.
So let's test that. If I go into a standard model right now and type generate an image of a bustling 1920s speakeasy, it's probably going to draw a dark room with people holding glasses.
Yeah, and it might look cool, but the details will probably be historically inaccurate.
So how does this information-level planner handle that exact same prompt?
Well, the planner looks at 1920 speakeasy and immediately realizes it lacks the generation context. So it generates a list of targeted questions.
Like what?
Like, what specific style of clothing and hats were worn by patrons in the 1920s? What did a 1920s cash register look like? What specific types of cocktails would be on the tables?
Oh, wow. So it explicitly identifies the gaps in the user's implicit request.
Exactly. And once it has those questions, it moves to the second level, which is content-level planning.
Assuming it actually finds the answers to those questions, which I know we'll cover in a minute, it has to physically structure that data, right?
It restructures the entire thing. It takes your short speakeasy prompt and all the historical answers it found and rewrites them into a highly structured generation specification.
Almost like a database entry.
Kind of, yeah. It explicitly maps out the subject, the attributes, the spatial layout, the style, and even any text rendering. It essentially acts as a world-class prompt engineer writing a massive JSON payload for the renderer.
And then there's the third level, generation level planning, which the paper says handles complex routing.
Complex routing and context allocation, yeah. Say a user asks for a comic strip with multiple panels. The generation level planner decides the dependencies.
Meaning what has to be drawn first.
Right. Do these images have parallel dependencies where they can just be generated at the same time? Or are they sequential, where panel 2 absolutely needs to see what panel 1 looks like before it can be drawn?
Ah, I see.
It also handles multi-turn scenarios, deciding what context from a previous chat message needs to be carried forward to the current render.
Okay, wait, let me push back on that. If the user keeps iterating over 10 or 20 turns and the system keeps appending all these detailed, historically accurate specifications, doesn't the model just crash?
You mean from context explosion?
Yeah, I mean, context windows aren't infinite, and visual context gets messy incredibly fast. How are they avoiding a complete memory overload?
Well, that brings us right into the second half of the pipeline, which is context grounding. This is how the agent actually answers the questions it asks and how it manages all that memory without crashing.
Okay, so how does it work?
Context grounding relies on 4 pillars. To answer your question about context explosion, let's look at the memory pillar first. The agent doesn't blindly concatenate all previous conversational turns into the prompt.
Ah, thank goodness.
Right. It performs what they call relevance-based context selection.
Meaning it's using something like vector embeddings to search its own memory?
Essentially, yes.
Yeah.
It uses semantic search to pull only the conversational history, user profile settings, or external knowledge base items that are strictly necessary for the current turn.
So if you spent 5 turns adjusting the lighting in panel 1 and now you were drawing panel 2, it prunes out all that lighting negotiation.
Exactly. And it only keeps the final character descriptions. It keeps the context tree trimmed.
Okay, so the memory pillar handles the continuity, but to actually answer those historical questions about the speakeasy, it needs the reasoning and search pillars.
Yes. Let's start with reasoning, because the paper highlights that it handles common sense, logical, and visual reasoning.
The visual reasoning is where the system really separated itself from standard models for me.
Or the maze example.
Yes. In their benchmark, there's a task where the user provides an image of a complex maze and prompts connect the green square to the red square.
Standard models fail that so badly.
They really do. A direct generation model, even a massive one, usually just draws a blue line cutting straight through the walls of the maze.
Because it's just predicting pixels based on the words connect and squares. It doesn't understand the rules of a maze.
But Qwen-Image-Agent actually solves the maze first.
It does. It deduces the path using text and spatial coordinates.
Mm-hmm.
The MLLM traces the route visually, outputting intermediate logic like go right from the green square along the top quarter, turn downward at the second intersection.
That is so cool.
It maps the solution in the context space first, and only then passes those explicit spatial instructions to the rendering engine. It completely decouples the logical problem solving from the pixel rendering.
And for things that can't logic its way out of, it uses the search pillar. I found it interesting how strictly the researchers partition knowledge here.
Yeah, the divide between common sense and dynamic facts.
Right. They separate common sense facts, which the MLLM is trusted to handle internally via reasoning, from precise or dynamic facts, which strictly require external search.
I mean, if you ask for the Amazon stock price on August 4, 2023, no model is going to reliably hold that exact closing price in its latent weights without high risk of hallucination.
This is not going to happen.
So the planner recognizes that as a dynamic fact. It extracts the keywords, hits a search API, summarizes the web result, and injects the actual numerical data into the context before generating the image of the stock chart.
It also searches for visual IP, right? Retrieving reference images for specific characters or real-world objects.
It does, yes.
But I have to push back hard on this. If you are an engineer, you know that handing an image editing model random pictures from a Google image search is a massive recipe for disaster.
Oh, absolutely. Editing models are incredibly brittle.
Yeah, like if you pull a reference photo of a 1920s cash register, but the photo has weird museum lighting or unrelated background noise, doesn't the model just adopt that visual bias and ruin the aesthetic of the final render?
You've hit on one of the most critical engineering realities the researchers discovered. In their ablation studies, they explicitly highlight that excessive image search severely degrades the final output quality.
Really? So giving the agent access to the entire internet actually hurt it in some cases.
It did. Current editing models and reference following adapters are nowhere near as robust as direct text-to-image generation. Those weakly related reference images act as visual poison pills.
Visual poison pills, I like that. So how did they fix it?
Well, they found that some baseline agentic setups tend to overuse image retrieval just because they can, which heavily distracts the renderer. To fix this, Qwen-Image-Agent strictly adapts the boundary of image search to the specific capabilities of its underlying generator, which is Qwen-Image 2.0.
So it puts guardrails on the search.
Exactly. The agent is prompted to only invoke image search for highly specific complex IP references, and it applies strict constraints to ignore backgrounds and lighting in the retrieved images.
That makes a lot of sense. So the final pillar of context grounding is feedback, because standard models are essentially drawing blindfolded, right? They can't see the image while they create it.
Right, it's a one-and-done pass.
Qwen fixes this by setting up a post-generation vision language model evaluation. It takes the checklist generated during the planning phase, looks at the final image, and just checks it off.
Yeah, if you ask for 5 red cars and it drew 4, the VLM flags the error, and that failure becomes feedback context injected into the next loop.
So we have this complete architecture now. Context-aware planning is the director breaking down the script. The grounding pillars, so memory, reasoning, search, and feedback, those are the location scouts and continuity editors gathering the materials.
It's a great setup.
But architecture diagrams on a whiteboard aren't enough. We need quantitative proof that this complex multi-step pipeline actually beats just prompting a massive monolithic proprietary model.
Which is exactly why they introduced IA Bench, the image agent benchmark.
Because existing benchmarks are kind of outdated for this.
Totally. They argue that existing benchmarks like Geneval are flawed for this era because they focus almost exclusively on final rendering quality and basic text alignment.
They don't test if a model can fetch real-time data or maintain a user's profile across a long conversation.
Exactly. IA Bench tests 17 real-world tasks across the 4 categories we just talked about: plan, reason, search, and memory.
And the evaluation criteria are brutal. It's a rigorous VLM-based checklist evaluation.
Yeah, they measure checklist accuracy, which gives credit for partial compliance, but the primary metric is pass rate.
And pass rate is strict. You only get a passing score if every single checklist item is flawlessly executed in the final image.
So a single mistake means a 0 for that prompt.
Exactly. And the results are what caught everyone's attention. Qwen-Image-Agent achieved an overall IA score of 45.4%.
Which is huge.
Yeah, because the direct generation baseline of their own Qwen-Image 2.0 model only scored 17.4%. Wrapping the exact same rendering engine in this agentic workflow almost tripled its capabilities.
It's just wild to see that kind of jump without changing the core weights of the renderer.
And it easily outperformed massive proprietary models like GPT-Image 1.5 and Nano Banana Pro, while completely crushing open source models like Stable Diffusion 3.5 and FLUX.
It also proved it wasn't just overfitting to its own benchmark. They tested it on external benchmarks like MindBench and Wise Verified, which test external knowledge and complex multi-step reasoning, and it sets state-of-the-art across the board there too.
See, if I'm building this system, I want to know where the load-bearing walls are. If I start knocking down pillars to save compute, does the whole house of cards collapse?
You're talking about the ablation studies.
Yeah, the ablation studies in the paper are super revealing here. When they removed the reasoning context, the reasoning score obviously dropped. But it also caused a massive cascading drop in the planning score.
Right, which seems counterintuitive at first.
Why does removing the ability to logic through a problem break the ability to plan a visual layout?
Because many spatial planning tasks rely on implicit mathematical or logical requirements that have to be deduced first.
Give me an example.
Take a task where a user asks to arrange the numbers 1 through 20 in a spiral pattern. The planning module can't just write a spatial layout for that out of thin air.
It doesn't just know what a spiral is natively.
Not in terms of exact coordinates, no. The reasoning module first has to calculate the actual coordinate matrix of what a 1 to 20 spiral mathematically looks like on a grid.
Oh, I see.
Yeah, if you take away reasoning, the planner has no logic to build its visual layout on, and it fails completely.
The interconnectivity is wild. But I want to zero in on their feedback loop because I think they are getting off easy here.
You think it's too simple?
Well, the paper explicitly admits to a bottleneck they call weak feedback supervision. Using a VLM to just check a Boolean true or false list of prompt requirements at the very end of the process feels incredibly basic.
It is basic.
It's like trying to grade a complex, nuanced thesis paper using a simple multiple-choice rubric. If the VLM says you failed to draw the speakeasy bar in the left corner, the model tries again, but it doesn't actually know why its spatial composition failed the first time.
The authors are very transparent about this being a limitation, to be fair. Right now, it is purely post hoc critique. The VLM just looks at the final output and gives a binary yes or no.
Which isn't enough for true scaling.
Right. If you want true test time scaling, that concept where giving the model more time to quote-unquote think exponentially improves the result, you need feedback that supervises the intermediate steps.
You need the director to step in during the shoot, not after the movie is rendered.
Exactly. You need the feedback loop to evaluate the information level planning questions. Did it ask the right questions?
Or evaluate the retrieved search results before the image is even drawn.
Yes, to filter out those poison pill reference images early. The authors suggest future systems will require explicit task-specific reward models at every single step, rather than just a generic VLM checklist at the very end.
Let's talk about the backbone dependencies, because you can't just plug any open-weight models into this framework and expect magic.
No, definitely not.
The system is highly dependent on having a frontier-level MLLM acting as the brain. They used GPT 5.50424 for their primary tests. When they swapped that out for a cheaper, weaker language model, the layout-aware planning completely fell apart.
It couldn't extract the correct search keywords or prune the memory effect.
And it is equally bottlenecked by the generation backbone.
Oh yeah, even if your frontier MLLM builds the most flawless, mathematically perfect context specification, if you pass that to a weak renderer, the system still fails.
A weak rendering engine simply cannot follow dense visual references or execute complex coordinate layouts, no matter how good the instructions are.
Exactly. The engine still matters.
So if you are an engineer listening to this and mapping out a production pipeline, you are probably screaming right now about latency and cost.
Oh, the cost has to be massive.
You aren't just doing a single pass through a diffusion model anymore. You are querying a massive MLLM multiple times, hitting external search APIs, scraping and summarizing web pages, running spatial reasoning, and executing VLM evaluations. How do they handle the sheer compute time?
They mitigated the latency using a DAG execution model, a directed acyclic graph.
Let's break down how that actually saves time in practice for our listeners.
Sure. So a DAG allows the system to map out which tasks are dependent on each other and which are independent, so it can run things in parallel.
Give me a real-world scenario.
Okay, for example, if the user asks for an image of a stock chart superimposed over the current weather in Tokyo, the agent knows that searching the web for the Tokyo weather has absolutely no dependency on hitting the financial API for the stock price.
There are completely separate queries.
Right. So instead of doing them sequentially, it splits those tasks into parallel branches, the DAG, running them simultaneously.
That's smart.
It also parallelizes the reasoning tasks. It calculates the math for the chart layout at the exact same time it fetches the images. Once all the parallel branches finish, the DAG merges the context back together.
Okay, so that significantly cuts down the wall clock time, but fundamentally, you are still paying for all those API calls.
Yes, it is undeniably slower and more expensive than direct generation.
Which means we are dealing with the classic engineering trade-off speed and cost versus accuracy and context awareness. The core takeaway from this deep dive into AI paper slop is that if you want reliable production-grade visual tools, treating image generation as a simple prompt to pixel mapping is a dead end. Real-world prompts are messy. Crossing that context gap requires a robust systems engineering approach.
And honestly, if we look at the trajectory of the entire AI industry, this paper leaves us with a truly provocative thought.
Does that up?
We are witnessing the dawn of test-time compute for visual models.
Right, like we saw with language models.
Exactly. In the language model space, we have already seen a massive shift toward models that spend more inference time thinking, planning, and reasoning to improve their answers before outputting a single token.
And now image models are adopting the exact same architecture.
They are spending inference time searching the web, checking their own memories, calculating spatial mathematics, and running internal feedback loops before they render a single pixel.
It really makes you wonder what the future of state-of-the-art image generation will actually look like in 2 years. Will the market be dominated by these massive, monolithic models trying to memorize the entire visual world and all of human history inside their latent weights?
Or will the future belong to much smaller, incredibly fast rendering engines that are orchestrated by hyper-intelligent language agents acting as art directors?
It's a fascinating structural question and definitely something to mull over as you build your own pipelines. Thanks for joining us for this deep dive into today's paper on AI paper slop. Keep pushing the boundaries of your own ML systems, and we'll see you next time.